So today we're going to start chapter 7. And chapter 7 is very similar to chapter 6 because it deals with compounds with pi bonds. So here chapter 7 is reactions of alkynes. Now, alkynes, as you know, have a very specific structure. So they have 2 pi bonds. So they're linear. You have this type of alkyne or this type. And we have here 2 pi bonds and 2 pi bonds. So these type of alkynes where there is an H at the end, these are called terminal or external, external. This one is called internal. So what is external and what is internal? It's that triple bond is in the middle of the carbon chain. Now, naming these compounds, it's already on the lecture note, so you need to learn how to name them, and I'm not going to spend time teaching you how to name them because it's kind of simple. But we need to first to look at all the reactions of these alkynes. But before we get to their reaction, we have to understand the difference between these two. So the whole chapter 7, we're going to be talking about external versus internal. And we need to compare their stability. So the internal ones are more stable. So why are they more stable? It's because the pi bond here, it's pulling these 2 carbons together. But what happens when you have alkyl groups, right here, these 2 alkyl groups, they have an electron donating effect. So here, the electron donating. So what does it mean if they're electron donating? Is they're like, even if these 2 carbons feel like they're stretched inside because of the pi bond that kind of squeeze them together, the alkyl groups are going to compensate that kind of strength or that pull on these 2 carbons. In here, we only have one side that has electron donating. So the difference is like internal ones, they have 2 sides that have electron donating. So that makes it more stable. In here, we only have one side that has an electron donating effect. So they're less stable. So what does it mean, more stable, less stable? It has to do a little bit with their reactivity. But both of them will react because they have pi bonds, and we already learned that pi bonds are side-by-side overlap, they're partial overlap. So we're going to start looking at the reactions of these alkenes, and the first one, just like we did with these alkynes, and just comparing to the alkenes in chapter 6, so this is chapter 7, compared to alkene, the first reaction was the addition. By the way, they all react in addition reactions, and the additions are electrophilic. Why? Because these pi bonds are nucleophilic, okay? So it has electrons on that surface. So they have to have addition reactions. And the first one, we're going to do addition of hydrogen halide. Now, to compare it to the previous chapter, what is a hydrogen halide? It's HX. For me, what's more important here is that whenever you have these additions, they're going to be electrophilic addition. You need to bring something positive to the pi bond. So we're going to call them electrophilic additions. So we need something positive. In this case, we are using a Bronsted acid. So HX is a Bronsted acid, and which means that the H will be added as an H+. So what is HX here? X can be, so here it's HF, HCl, HBr, and HI. So they all work in here. Now, how does it work? The mechanism. As usual, we always want to see how these reactions work in terms of mechanism. So the first step, so I'm going to start with the external alkyne. I'm going to look at external alkyne. So we take an R, C, triple bond CH, and this is a Bronsted acid. I'm just going to show you this is Bronsted acid. We always need an acid, something positive on this pi bond. So we're going to bring the Bronsted acid right here. Now the mechanism here is a little bit, it's not very clear, but they think that this is how it works. So basically, what you need to understand is at this step right here, the hydrogen kind of sits between these two carbons. It just kind of like fits right into this, between these two. And so as a result, you're going to have this and this. But there is an intermediate here, and you're going to see an R, C, C, H, and notice that I removed one of the pi bond, and what is the intermediate is like that pi bond is started to break, and then you're going to form new bonds with the hydrogen. But these are still not complete bonds, sorry, so it should be kind of dot, okay? And the Cl here has to leave at this point. So this is called a pi complex. So what is really a pi complex? It kind of looks a little bit like when you have hydrogen with palladium, when you're adding the hydrogen on alkenes. It's kind of like temporary bonds that are loosened and bonds that are partially formed. And you might say, hey, wait a minute, hydrogen cannot have two bonds here. But again, this is all kind of like in between scenarios. So what happened next? If this opens, we're going to have a Cl minus here. So in the HCl being a strong acid, you will produce Cl minus in the mixture. So what's going to happen is the Cl now comes to the carbon, and then this opens, and then this opens. So what it means is like now this carbon, the right one, will be bonded to the H, and this carbon will be bonded to the chlorine. So we end up with an R, C, Cl, double bond, C, H2. Now, I showed here that the chlorine adds to the left carbon. What if chlorine adds to the right carbon? Okay, so if it adds to the right carbon, so I'm going to use this as the pink. If it adds to the right one, so this adds here. So now we have the arrows are like this. And so the hydrogen will attach to this. And you see how we have two arrows, this comes here. So in this case, this opens like this and this opens like this. So the green one will give me R, C, H, and then C, Cl, H. I'm showing you here we have a double bond. So what I'm supposed to show really is that they are opposite from each other. So this is called an anti-addition. So if the pi complex is on the top, the chlorine comes on the bottom. So that's the reason we have to have this. So now the question is, which one is the real product? Is the chlorine going to add to the most substituted carbon or the least substituted carbon? The answer is, let's see what is the kind of intermediate. In here, for the pink one, the intermediate is an R, C, C, H, and then I have an H and a Cl. So what you need to see is that you have this happening. And then there's a double bond. So for the pink one, we have this. For the green one, we have R, C, C, H. And then I'm going to put the Cl here and the H here. So the green stuff is kind of the intermediate. It's like the process when these bonds are being not completely formed. Now you can see that in this case, this, when the hydrogen adds here, this is our carbocation. So this is a delta plus. And in this scenario, this is our delta plus. So it's obvious that this delta plus here is, as you can see, it's attached to two substituents. So this is a secondary, and the delta plus here is a primary. Okay, so this carbon is attached to one carbon, this one is attached to two. So this is primary and this is secondary, which means that this is more stable. So this is the major product. So that's the product. So this is adding HX. When we add HX, we're going to have, first step is formation of a pi complex. Second step, attack of the X minus. And the result is the halogen will add to the most substituted carbon, not the least substituted carbon. So this is the reaction on an external alkene. Now, this assumes that we have 1-to-1 ratio, 1 mole of alkyne for 1 mole of HX. What if we don't have just addition of halide? We're going to put an excess. What if we put more than 1-to-1 ratio? So that would be my second page here. So 2, addition of hydrogen halide, but we're going to put it here, excess. So if you see the word excess, it means it's not a 1-to-1 ratio. You have more HX than the alkynes. So let's keep going with the external alkene. And I didn't go with the internal, it's okay. We're going to get back to that one. So if I have an external alkyne, and I start with an R, C, triple bond, CH. And the first one is the HCl. So we already established the first step is that pi complex. So it's R, C, double bond, CH. And the pi complex is this bond is breaking and these two bonds, kind of a semi-pseudo bond forming there, and the Cl. So I'm just repeating what we did earlier. So this has to open. So we already established that the chloride here will add to, it comes from the bottom, and it will add to the most substituted carbon, because this would be the highest carbocation. This primary, this is secondary. So this adds here, this opens, and this opens here. So we end up with R, C, Cl, double bond C, H, H. So it's an anti-addition. See, these two are opposite, so it's anti. That's the first step. Now, if it's excess, it means we're going to go again. So we're going to take this substance. So now it's an alkene. C, H, H. So it's like adding HX on an alkene. So we're going to do HCl. Now this is what we learned from the previous chapter. Where is the H going to add, to the right or to the left? If we add it to the right, this will be the carbocation. If you add it to the left, this will be the carbocation. It's obvious the H will add to the least substituted. So the pi bond open takes the H, this opens. You end up with an R, a C, R, Cl plus, C, H, H, and H. And then your Cl minus will attack here. And we get R, C, Cl, Cl, CH3. So you see, what's important is that the first chlorine adds to the left, right here. The second chlorine adds to the same one. So this is called a geminal dihalide. Geminal means on the same carbon, you have the two halogens, okay? So if you have an excess of HCl or HX, you're going to end up with this. Now let's try an external alkyne, okay? So if I go with internal alkyne. Now you notice how here in the external we did the first part and then the second. So since I didn't do the internal for this, it will appear here anyway. So let's try the first step. So what does it mean in internal alkyne? So let's say I'm using this one. I have CH3 on one side, and I have C, C, CH2, CH3. So what is the first step? We're going to have HX or chlorine, it doesn't matter. So the first step, we're going to have the pi complex, so it's CH3, C, double bond C, CH2, CH3. And then what is the pi complex is all these semi or pseudo bonds with, I'm going to use Cl here. So the question is, now here it's an internal, it's no longer external. Would it make a difference if the carbon adds on this side or that side? The answer is if it adds on this side, if the hydrogen adds on the right, this is secondary carbocation. If it adds on the left, this is also secondary. So we're going to have both, okay? So what is the process here? This opens here, and this goes here, this opens. And your Cl minus, we have two options. It will add to the left, and I'll have the green, or it will add to the right, and I'll have the pink. So if the chloride adds to the left, you end up with C, Cl, CH3, double bond, C, H, CH2, CH3. If it adds to the right, which is the pink arrow, we're going to end up with CH3, CH, C, Cl, CH2, CH3. So if it's not an excess, that's what you get. And you get exactly 50-50. Why 50-50? Because this will give us a secondary and a secondary. So we're going to have 50% of this and 50% of that. So adding just 1-to-1 ratio of HCl for the alkyne, we get 50-50% of these two products. And it's going to be no matter what you have on each side, you're going to have 50-50 because both sides will give you secondary carbocation. Now, what if we put an excess? So this is the first step. And like here, this is just 1-to-1 ratio. Is this part. And see. And here is excess, meaning you go again. So this is the same thing. This is 1-to-1 ratio. And then we're going to do the next step, which is taking these and do an excess. So what are our product there on page 3 here? So I have CH3, C, Cl, C, CH2, CH3, H. So that was the green product. The other one is CH3, CH, C, Cl, CH2, CH3. So if we add another HCl, we already know that in this scenario, the H, this is like the previous chapter, that's chapter 6. We have a double bond, you have HCl. So the pi bond takes the H. I should use the green because this is my green product. So the pi bond takes the H. This opens. And we're going to get, now here, the pi bond opens, takes the H, and this opens. So what do we get in this scenario? We're going to have CH3, C plus, Cl, C, H, H, CH2, CH3. And in this case, we're going to have CH3, C, H, H, and then C plus, Cl, CH2, CH3. The last step now is the Cl minus. So we have a Cl minus. We have a Cl minus here. And what happened is this attacks the carbocation. And we end up with a geminal. So it's going to be CH3, CH2, and this is CH2, and then C, Cl, Cl, CH2, CH3. So that's the product if we do the pink side. And the green will give us, so this attacks here, and we end up with CH3, C, Cl, Cl, CH2, CH2, CH3. So again, we're going to have 50% of this and 50% of that. And this is called a geminal dihalide. So this is a geminal, meaning the H's is always going to add on the same carbon, the Cl will add on the same carbon. And all of this is in the presence of excess HCl. So if we don't have excess, we stop at one addition, 1-to-1 ratio. That's the scenario. But if you have an excess, you're going to go again, and that would be the second addition. So if you remember, we did this in the previous chapter where we added HCl or HBr on an alkene. Now we did the same thing with an alkyne. The only difference is the alkyne can go twice if we put an excess. We also did the reaction of a halogen. So just H2, or sorry, this is page 4, just checking my pages here. So this is check for page 4. So we're going to now add addition of let's say X2 in CH2Cl2. So it means that we're adding a halogen in the presence of a non-pole product solvent. This is exactly what we did. So it can be this or CCl4. So this is what we did for the previous chapter. So we're going to start with the external, and then we do the internal. And just like the previous case, it all depends on how much of the halogen did we use. So I'm going to start to stay consistent with the previous scenario. We're going to look at external alkyne, and we're going to do 1-to-1 ratio. Okay, so this would be 1-to-1 ratio, meaning 1 mole of the alkyne for 1 mole of X2. So how does it work? I'm going to take, let's say this is my external alkyne. It's CH3C triple bond CH. So you can see it's external. And we're going to bring Cl2. So just like the previous example, we had in previous chapter, we call it the bromonium ion or the chloronium ion. So here we're going to have the same thing. The pi bond opens and docks on the empty orbital. This docks here and this opens. So you end up with CH3, C, Cl plus. So this is just like that pi complex, but this would be a chloronium complex. Okay? And now what do we have left? We have here a Cl minus. Okay? So if I have a Cl minus, the Cl minus will add. It really doesn't matter if it adds to the left or to the right because we have the 2 chlorines here. So if I add it on this side, this opens. Or if I add it on that side, the other one opens. But in the end, we're going to end up with this a pi bond, but it's going to be a cis, a trans, no matter what. So you end up with C, Cl, CH3, and then C, Cl, H. So no matter what, it's going to be an anti-addition. Now, we did this 1-to-1 ratio. How about we do excess? Excess means it goes again. So for 1-to-1 ratio, we stop there. For an excess Cl2, we have to keep going. We take this and we add another Cl2. So we're going to have C, Cl, CH3, C, Cl, H. And just like the previous scenario, we're going to have the chloronium ion So the pi bond opens, this opens, and then we end up with C, Cl, CH3, and then we have a Cl minus here. And what is the Cl minus going to do? One comes one side, the other one opens, and we end up with C, Cl, CH3, and then C, Cl, Cl, H. So that's what we end up with, 2 additions on both carbons. So we are going to have 4 chlorine altogether. That's in the presence of excess chlorine. Now, how about an internal alkyne? Will it make a difference? So you see here, we don't have any preference because we have the same substituent adding on both sides. So there is no preference left or right. And that is also the same with internal. So I'll show you right now an internal alkyne, okay? I'm going to go back to the previous one. So for internal alkyne, and we're going to do also the 1-to-1 ratio. What I mean by 1-to-1 ratio is 1 mole of the alkyne for 1 mole of Cl2. So if I take the CH3, C, triple bond C, CH2, CH3, we can have the same substituent or different ones. It's just to show like if it makes any difference by adding external versus internal. So we have a Cl2 here. Now remember, we already established in the previous chapter that this works for chlorine and bromine. It doesn't work for iodine because iodine is too big for this bond. So we have an empty orbital. I know the book doesn't show that, but you need to see that we have to have an empty orbital to get this going. We always need an acid. In the previous scenario, when we had HX, it was Bronsted. This is a Lewis acid. So you still need a place where that pair of electron has to sit. So in this case, it's the empty orbital. In the previous case, it's the H that takes it. So we have Cl, C double bond, plus, and then CH2, CH3. And then the next step, now we have the other Cl minus. And it's also an anti-addition because the side is crowded, so you have to have the Cl come from the other side. Now, what are our options? If the Cl adds to the right, this one opens, or I can have the Cl adds to the left, and this one opens. So the green product would be CH3, C, Cl, C, Cl, CH2, CH3. The pink product would be C, Cl, CH3, C, CH2, CH3, Cl. So if you flip them like this, if you flip this 180, you get exactly the same. So it's the same product, okay? So it's exactly the same. Now, what if we put an excess? It means we're going to take this. Since they're both the same, do you see, like if I flip it 180, the CH3 would be on the top, the Cl would be on the bottom, and vice versa. As long as you know that this is an anti-addition, you will get exactly the same product, whether that one chlorine attacks one side or the other. Now, for an excess, we have C, CH3, Cl, So I'm going to bring 2 chlorine here. And then this opens, this comes here, this takes the chlorine. And then we have CH3, CCl. And then now we have the other Cl minus. And again, it really doesn't matter whether it lands to the left or to the right, because in the end, each one of them will have 2 chlorines. So there's no chirality here. So this opens, and you end up with CH3, 2 chlorine on the left, and 2 chlorine on the right. And then CH2, CH3. So you see here, whenever you have an internal or external, you're only going to end up with 1 product because you end up with 2 chlorines on each side. Okay, what's next? We did this in the previous chapter. We added HX, we added a halogen in CH2Cl2. We also added water. So let's see how water adds to alkynes. Okay, so this is interesting, adding water. So addition of water. Now, just like the previous case, you can't just add water. You always have to use something electrophilic. Water is not electrophilic. Water is a nucleophile. So we need the acid here. So here it's addition of water in the presence of a catalyst. So here it's always acid catalyzed. Now, what type of acid here? It's always a Bronsted acid, which is sulfuric acid. So let's start with the external, okay? Remember how the difference between this chapter and the previous one is we don't have the situation where it's external versus internal. Here, it might be different. So the external, I'm using the same example as previously. And I'm going to use sulfuric acid. So sulfuric acid, if you remember in the previous chapter, if it's a catalyst, I'm going to circle it to show that I have to get it back. If it's a catalyst, you have to get it back. So of course here you're going to have that pi complex, you know, the H will, this one will open, just like the previous case. So you're going to end up with a pi complex. So it's CH3, C, H, C, double bond, H, and then this thing will be plus O SO3H minus. But since this is a catalyst, you might say, oh, this adds, but it's a catalyst, which means we don't have a lot of it. So, but if we add water, water is the solvent. So here we're going to have H2O ready. So first you need to add an electrophile, something positive, and then the second step, you're going to add water. So the question now, where would the water add? To the right or to the left? This is just like the previous case when we did HX. The hydrogen has to be on the least substituted because this will be a better carbocation. So if this opens, the carbon here, sorry, I forgot to put more dots. So we're supposed to have the pi complexes like this. We have to have 3 bonds. The hydrogen has to land on the right one because this will be a secondary carbocation, whereas this one is a primary. So this opens, and now the water has to add on this side. So end up with CH3, CO, H plus, and then CHH. Okay, but this is positive, so that's when our catalyst comes in. It's deprotonation. This is also similar to what we've done in the previous chapter. And you end up with CH3, COH, CHH. This is called an enol. So what is an enol? It's an OH that's on a carbon on a double bond. Okay. And of course, we have here H2SO4. So you see that's the catalyst, we get it back. Now this enol is not stable. So here's what happened. That enol, I'm gonna write it here, to have CH3, OH, CHH. What happened is the product acid here, we still have acid there. So we have HOSO3H. Your book might use H3O plus. It doesn't matter whether you use the sulfuric acid or you put H3O plus. You know from the previous class that sulfuric acid in water will give H3O plus. So here's what is interesting. This goes down here and this takes the H. So we end up with this COH plus CH3, and then CHH. And you all know that this is not stable, so we have also the OSO3H minus, which is the product of this. We'll grab the H, this opens, and we end up with CH3, CO, CH3, plus H2SO4. So this is an enol, this is a ketone. Okay? So what is the difference? Which one, why do we have to keep going? You see here, we have a double bond between two carbon atoms. And here we have a double bond between a carbon and an oxygen. We know that oxygen is more electronegative, which means that it's going to pull the electron. So this is more stable. A CO bond is more stable than a CC bond. So this would be your major product, okay? So it doesn't stop at the enol, it's gonna give you the major product, which is the ketone, okay? So this is the addition of water on an alkyne. And the process here, so page 7, we saw that a CH3 COH double bond CHH. This is the product, this one. I'm rewriting it here. And the final product is CH3 CH3O. So this is called enol. This is called ketone. This ketone comes from the enol and the equilibrium is shifted towards the ketone. So you need to learn that every time you add water to any alkyne, you always going to end up with an enol, meaning one H will go on one carbon and OH will be on the other carbon, so you're going to have a double bond with H and OH. But this is not very stable. a C-C double bond is not stable because it's nonpolar. Here, the oxygen is more electronegative, so it's going to pull. So that polarity of this bond makes it even more stable. A CO double bond is more stable than a CC double bond. And this process, going from enol to ketone, it's called tautomerization. So the process is called tautomerization. And these two, the enol and ketone, are considered tautomers. Okay? So what is tautomerization? It's really the process. So it's the keto-enol interconversion. So every time you have keto-enol conversion, interconversion, that's what tautomerization means. And I should put a bigger arrow towards the ketone, a shorter arrow towards the enol. So that's what happens when you add water to an alkyne. So to summarize it, if I take an external alkyne and I add water in the presence of sulfuric acid, we're going to end up with an RCOH, CHH. So you see water here, and OH comes this way, and the H goes the other carbon, and we have a double bond, and that becomes a ketone. So the H moves here, and the double bond moves here. So that's how you know how to write. So basically, to write an enol ketone tautomerization process, the H, this H will move here, this bond will move here, and we end up with RCO, C, H, H, and H. So with the external alkynes, so this is an external one, we're always going to end up with the ketone, and the ketone will always have a CH3 on one side. Okay, so that's the hydrolysis of an alkyne that is external. So let's try now an internal alkyne. So we're going to try the same one as in the previous scenario, so we're consistent. This is an internal alkyne. So how does it work? We have CH3, C, triple bond C, CH2, CH3. And the first step is that HOSO3H, we're going to create that pi complex, double bond C, CH2, CH3. The pi complex is like the third, this pi bond is starting to open and the hydrogen is starting to attach here. And then OSO3H. So this leaves. And at that point, you're going to bring the water. Now, what are the options? The water can come to the left. So this opens and this opens, okay? And also this opens. So the green one gives me this path. Or it comes to the right. So this opens, and that opens. And we have this. So the green one, the OH will be on the carbon on the left. So it's going to be C, CH3, OH, H plus, and then a double bond C, H, CH2, CH3. Remember, it's an anti addition. It's always anti. meaning the H is on the top, the OH on the bottom. Okay, it's always going to be anti whenever you have a Bronsted acid. On the pink side here, the water will attach to the right carbon. So we're going to have OH, H plus, and then CH2, CH3, and then a double bond C, H, CH3. Now what happens next, that catalyst, we need to generate it again. So it's going to take the H, so it's going to be deprotonation. So the pink side, this takes this, and we get, and the green side is, this takes the H, and we get this. So on the green side, we have this enol, on the pink side, we're going to have this enol. And of course, in both cases, we're going to have H2SO4, which is the catalyst, okay? And of course, here I have H2SO4. But we know that this is an enol. This is an enol, and enols are not stable. So this side will give us the ketone. This side also will give us the ketone. So what ketone? Remember, the H moves here, the double bond moves here. So I have C, CH3, double bond O. So the bond forms here and the H moves here. So I have here then CH2, CH2, CH3. This is the carbon here that had one H, and then it adds another H, so it becomes CH2. On this side, this H moves here, and the double bond moves here. So we have CO, CH2, CH3, CH2, CH3. So you see here that this ketone versus this ketone, this has two ethyl groups. So this is a diethyl ketone, but this one has a propyl on one side and a methyl. So it's going to give us two products, and it's going to be 50-50. So with an internal alkyne, we're always going to end up with two ketones, and it's going to be 50-50 of each. So remember that that's the scenario here with an internal. Internal, they always give us kind of two products. Okay, so now what's next? What is next is that the addition of water is not a very, it's not very reactive. Adding water to an alkyne is not something that works very well. So the best thing is to make it go fast and better. We use, instead of sulfuric acid as the catalyst right here, we can use a Lewis acid that's better than sulfuric acid. So sulfuric acid is a strong acid. It's a Bronsted acid. So the first step is to create a pi complex. Now, what if we bring a Lewis acid, which is an atom with an empty orbital? Now, what's good about the next scenario is that it goes fast. It's more efficient. But what's bad, it's not, it involves nasty chemicals. I'm going to show you that. So we're going 9. So it's hydrolysis or addition of water. But instead of using sulfuric acid, we're going to use mercuric ion catalyzed. So you already know that mercury is a nasty chemical. But here, if we use mercury to these reactions, it works better because it's a good Lewis acid. So how does it work? So let's first do the external. Okay, so external means I'm going to bring the CH3, C triple bond CH. And what is the mercuric ion? It's really Hg2+. Now, mercuric ion is a Lewis acid. It means it has an empty orbital. So what happened here, the pi bond, and it also has a lone pair there. So the pi bond docks here, and this goes here. So we end up with the mercurinium ion. So this is called mercurinium, just like bromonium and chloronium. This is called mercurinium ion. And then now our next step is to bring water. So I have water here, because remember, it's all about addition of water. So the question is, where would the water add, to the left or to the right? The answer here, it's really just like the hydroboration in the previous chapter. So mercury is a pretty big atom. So if it's a big atom, it doesn't want to be in a crowded space. So the left carbon here has a methyl group. So this side is kind of crowded. So the mercury will prefer to stay on the right side because there's less steric hindrance. So the only way here is the oxygen adds here and the mercury opens. So you end up with this CH3, COH plus. And then we have a double bond C. And now the mercury is plus. It was 2 plus there, now it's 1 plus. And then H. Now I hope you understand the reason it sits on the right side, it's because of steric hindrance. Okay. Now what should we do here? This is not stable, so we bring another water molecule. We need to deprotonate. So that tells you that we need also sulfuric acid. So in these reactions, we're going to use sulfuric acid and mercury. And the reason we use both is to make it faster. The mercury makes it a lot faster. So we end up with CH3, COH, double bond C, Hg plus H. So this is also an enol shape. You remember C double bond COH? That's an enol. This is called a mercuric enol because it has a mercury and it's the enol part. So this part is what we call enol. Now, what does an enol do? It's not stable, so it has to go to a more stable position. So what is it? It's ketone. So what does it mean? This bond moves here, this hydrogen moves there. So we have an enol ketone. Remember, every time you do this, the double bond becomes between C and O. So I have C double bond O. And this H has to transfer there. So here we have CH3. And on this side, we have CH2 and then the mercury. Okay. So now what's the next step? So this is mercuric enol. This is a mercuric ketone, because that's the ketone part. and that's the mercuric. We don't want this, so we want the mercury out. So all we have to do is just bring water in, okay? So if we bring water in, because here it's H3O plus, or the acid, so because that's the product of this step. So this takes the H, this opens, and we're going to have CH3, COH, plus CH2Ag plus. So the next step is this folds, this can open. So you end up with CH3, COH, CH2. So this is again an enol. And then an enol transforms into a ketone. The H moves here, the double bond moves there. So CH3, CO, CH3. And every time we have an external alkyne, it's always a CH3 at the end, always. So what is the difference between this scenario and the previous one? As you can see, in the previous one, the external, right here, we got the same thing. So if I start with CH3, CH3, CH3O, we got exactly the same thing, CH3, CH3O. So what does it tell us? It's exactly the same product. The only difference is this is a lot faster because we're using a very strong Lewis acid. So starting with mercuric ion, we're gonna get the reaction to go a lot faster, especially for external alkyne, because external alkynes, we already said that they kind of react slowly. So mercuric ketone will give us a mercuric ion catalyzed. The process is kind of, the outcome is the same, except that it's a lot faster. So you can refer to this on page 301, which shows the detailed mechanism for an external alkyne that is not symmetric. That is an external alkyne because it's kind of slow. Okay, so now what's next? If we keep consistent with the previous chapter, we added water, we added halogen, we added HX. We also did the hydroboration oxidation. Now, in the previous chapter on an alkene, we end up with alcohols. In here, you saw that with an alkyne, we end up with ketones, okay? So what if we add hydroboration oxidation? So this is page 10. So this is hydroboration oxidation on alkenes, on alkyne. So let's start with an external. So what external did we use? We used CH3, CH. And then what is the hydroboration? Well, you end up, you start with BHR2. So in this case, we have Br2H in THF. That's the solvent. If you remember, it says first step is, but in the previous scenario, we didn't have HBr2, we had BH3. Here we have HBr2, R meaning any kind of alkyl group. So what happened here? This side is pretty bulky. So if it's bulky, and this is a Lewis acid. So what does it mean if it's a Lewis acid? It means the pi bond, this pi bond, docks right onto this, and this goes to the carbon. In this scenario, they're on the same side, And the boron has to add on the bulkiest, on the less substituted. Why? Because this is bulky. So you're going to end up with C, CH3, H, and then C, H, Br2. So that's the first step. That's the first step is hydroboration. Hydroboration gives us this. And I want you to pay attention here. This bond is here. And this bond here is here. So this is called syn addition. So it's always, hydroboration is always syn, meaning the two come on the same side. Now, what is the second step is oxidation. So what does it mean? The boron here will take off and an OH comes there. So the second step is oxidation. So what does it take to do the oxidation? You need OH minus, H2O, H2O2, and don't worry about the detail of it. All you need to know is that you're going to end up with C, CH3, H, C, H, OH. So with an oxidation, the boron takes off and you get that. Who cares about what's next, what's with that? So again, this is an enol. Remember, an enol is this part. And an enol is never stable, so the H moves here, the double bond moves here, and it goes to a ketone. So we're going to have the double bond is now on this carbon. But you notice here that we have CH3, CH2. So this is an aldehyde. See, because this H, if we look at the lone pairs, we already said that this H right here, this H moves on this carbon and this goes here. So you end up with an aldehyde. In the previous scenario, when we added water, we didn't get an aldehyde, we got a ketone. Now, what if it's internal? So first step, with the same thing, CH3, C, C, CH2, CH3. So the first step is BHR2 in THF. So on one side there's an H, on the other side there's the boron. Now in here, which side will add the bulky part? So boron will stay on the less bulky. So you see this side has less stuff going on than this side. It's not about primary, secondary. It's really about how crowded is the area. So in this case, the boron will attach to the less crowded section. So this opens here, this goes here. So I have CH3, C, Br2, double bond C, H, CH2, CH3. Okay? But it can also add to the other one, but it's going to be almost like 50-50 almost. Okay? But not exactly, because you will have a little bit more of this. So here I'm doing this side, but we can also have, so I'm going to put the pink part, but we can also have, with less amount, the boron will sit on this side, and so you're going to have CH3, CH, C, Br2, CH2, CH3. Now what happened with the second step? So the second step, which is oxidation. So what do we get here? This takes off and you're going to have an OH. So you have CH3, C, OH, double bond CH, CH2, CH3. And on this side, you're going to have an OH here. So it's going to be CH3, C, H, double bond, C, OH, CH2, CH3. Again, this is enol, enol. So both of them will give us a ketone. So which side the double bond moves here, the H, this H moves there. So we'll end up with CH3, CO, and then here we're going to have CH2, CH2, CH3. And on this side, the double bond moves here, the H moves here, so you're going to end up with CH3, CH2, CO, CH2, CH3. So if it's external, when it's external, it always produces an aldehyde. If it's internal, it always produces ketones. And we're going to have two of them, but it's obvious that the less crowded one would be more than this one. But we're going to have ketones. So hydroboration oxidation for an external will give us an aldehyde. For an internal, it gives us just ketones. Okay, so what's next? We did hydroboration in the previous chapter. Then we did addition of hydrogen. So, which is called reduction. And basically, this will be it in terms of reaction. So we're going to have addition of hydrogen on alkynes. Which is called reduction. We're not doing oxidation. Now, in here, the good news is like you just have to know the product. The mechanism is kind of complex, so you don't need to know the complexity of the mechanism, but you need to know what is the difference between the scenarios. So let's start with an internal alkyne. So again, internal. I'm using exactly the same substance, so we are always consistent. So we need to add H2. So what does it mean add H2? It goes on each carbon an H. Now, if you use a palladium catalyst, so this is, it all depends on what is the catalyst. So if you use palladium that's spread out on a carbon powder, so that's what it means, PDC. Palladium is pretty expensive, so what they do is they kind of crush it in the presence of charcoal, and it kind of disperses it on a surface, and then they run this as a gas and this as a gas, and when they come out, these two are reacted. So the first step, you're going to end up with an alkene. So these two are the H2. So it's a syn addition. But then it keeps on going. It doesn't stop. And you end up with CH3, CH2, CH3. So every time you start with an alkyne and you use palladium as a catalyst, you end up with an alkane. It doesn't stop to the alkene. It goes all the way to the alkane. Now let's look at the internal. I'm sorry, this should be external and then internal. So CH3, C, CH2, CH3, just like the previous scenario. If you use palladium in the presence of carbon, first step, you're going to end up with an alkene. And then the second step all the way to the alkane. So it's going to be CH3, CH2, 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 CH3. So we have the CH3 here, and then 1, 2, 3 CH2s, and then a CH3. So in both scenarios, you're going to end up with the alkane. Okay? That is if we use palladium in the presence of carbon. Now, palladium is very reactive. That's the reason the reaction keeps on going, okay? But if we want to make it less reactive, what if I want to stop right here? What type of catalyst do I use? We can still use palladium, but it's going to be called Lindlar Catalyst. So let's try it. So if I have CH3, CH, and you use hydrogen in the presence of Lindlar. So what did Lindlar do? He kind of made that surface dirty. So he covered up a little bit of that palladium. So not all of it is exposed, not all of it is pure. It's probably a mixture of palladium that's slightly oxidized, or they mixed some other stuff. So it's less reactive. So Lindlar, it's still, when you see the term Lindlar, it's really modified palladium catalyst, which is a little bit dirty. So what do you get? You only get one addition, okay? So that's what happens. And it's syn addition. So these two add on the same sides. It's syn addition. So you end up with the cis no matter what, okay? You end up with the H's there. What if it's internal? Here, by the way, sorry, when it's external, we don't have cis and trans. We just have an H on each carbon and we're done. But if it's an internal, like we go to the previous scenario. So Lindlar limits the reaction to one time, not twice. So we end up with CH3, CH, C, CH2, CH3, H. So that's also a syn addition. And it's cis. So it's always going to be cis no matter what. Okay? Now what if we want the trans? Is there a way to create the trans? The answer is yes. And that's the last reaction to learn in this chapter before part 2, which I'll do in part 2 of the video. So what do we use to get the trans? So you see, if you use regular palladium carbon, you go all the way to the alkane. If you use Lindlar, you're going to get a syn addition, but you get only the cis for an internal. Of course, there's no point in using Lindlar. We use Lindlar just to stop it there. But if I want the trans, I don't need to use an external, I have to use an internal. But I can show you anyway in case of external. So go back again to the same molecule. Now in here, we don't use H2. So that's the difference. So first step, the catalyst is sodium or lithium. And you use NH3 liquid at minus 78 degrees Celsius. So what happened is the source of H's here is from NH3. So NH3 is going to give the H's, gives the first one, then the second one. When it gives the first one, it becomes NaNH2. And when it gives the second one, you have enough metal there to sustain that negative charge. So you end up with C, CH3, H, C, H, H. So it's going to be the same, even though it is an anti-addition, okay? So it is anti, but in this scenario, since we don't have substituent, it doesn't make any difference. But if it's an internal alkyne, CH3, C, C, CH2, CH3, and we use the same stuff, which is sodium or lithium, in the presence of liquid ammonia at minus 78 degrees Celsius. It's going to be an anti-addition. So on this side, the left side, I have CH3. On the right side, I have an ethyl, but they're going to be anti-addition. So the two H's add opposite from each other. So both of these are anti, but this is the trans. So that covers all the reactions of alkynes in terms of additions, okay? So we covered all the additions on alkyne, and to summarize, we can add an HX, which is a Bronsted acid. We can add a halogen because the halogen can be both an acid and a base. We added also water in the presence of sulfuric acid. We added water in the presence of mercury. We added water, it's a hydration through hydroboration oxidation. That one produces aldehyde or ketone for an internal. And finally, we added hydrogen. So this covers pretty much the biggest part of the chapter. And what is left is really synthesis. So we're going to start with the real stuff here. How are alkynes used? And especially in particular, external alkynes. So I'm going to stop right here, and then we'll do the second part later. Thank you.